yesterday we were looking at squares, we were looking at rectangles. Today we'll be doing the same thing, but we will be looking at triangles. So, for example, it's not really wanting to cooperate here. If I want to change this to an equilateral triangle, I don't want it to look like that. There we go. You can see that if I use a triangle, I'll get a different shape than versus having the square, which we were looking at yesterday. This one won't do semicircles for some reason. But think of like only the top half of this here. We'll do some right triangles with the base as one leg. That would look like this. That one's pretty cool looking. It looks like a shark fin or something there. So that's what we will be looking at today. You could even do things like a polygon. That one starts to get way more complicated than we want to have to deal with, and they're not going to ask you that on the exam. So we're not going to go there, but we could. When I used to do the project, you can see those, like this one right here with that's like a smiley face, the orange part. Those are trapezoids. So that one was really hard to do because you had to use the area of a trapezoid as your function. So that was a tough one to do. But you could use any shape, and we could figure it out. It's just going to take a lot more than they're going to ask you to do here. So what we'll be asked to do are some triangles and some semicircles, in addition to squares and rectangles, which we have already looked at. So a lot of what you do is the same as what we were doing yesterday. The difference is the area formulas that we're going to be looking at are going to be different. So, example 1 says a solid has a base that is bounded by the curves y equals x squared and y equals 2 minus x squared in the xy plane. Cross sections through the solid perpendicular to the base and parallel to the y-axis are semicircular discs. Find the volume of the solid. So the first thing I want to know is I want to know what my base looks like. So like whenever we're looking over here at that website, in this case, this was your shape of your base. If I turn this sort of upside down, there's the bottom of what the shape is going to look like. So we have to get a good idea of that by sketching ourselves a graph. This one's a fairly simple one, so they would probably expect you to be able to do that graph on your own. So if I've got y equals x squared, that is going to be a graph that looks like this. And then I've got 2 minus x squared, so that would be a graph moved up 2, but it would be upside down. So I'm going to get something that looks a little bit like this. So if I try to graph that a little, it should, there's your x-axis on this, so it should just be like first and second quadrant. And if I graph this here, if I graph y equals x squared in blue, that would look like this. You're just plugging in some points into x squared. 1 squared is 1, 2 squared is 4. You'll get this graph right here. If I do 2 minus x squared, if I plug in 0, I get 2. If I plug in 1, I will get 1. If I plug in negative 1, I'll get 1. So that graph will look like this, roughly. And so this is our bottom, our function. very similar to what the one on the graph looks like. It's just moved up a little bit. So, next I want to think, do I need to do this problem in terms of x's or in terms of y's? And to do that, I need to look at this phrase right here where it talks about either the x-axis or the y-axis. It tells me parallel to the y-axis. Is that in terms of x or in terms of y? Feels like it should be in terms of y. But the ones we were doing yesterday said perpendicular, not parallel. So if we're parallel to the y-axis, I don't like it when they do this because I think it's unnecessarily tricky because they usually say perpendicular to an axis. So parallel to the y-axis, something that's parallel to the y-axis, if we think of taking a little strip right here, would be a vertical slice right there. And in this case, we're not going to be making squares out of that. We'll be making semicircles out of that. So if I want to call, I'm going to still call this right here S. You also might want to call it D because it is the diameter of that semicircle. So D would not be a bad thing to call it. Do not call it R. It is not the radius of that semicircle. Okay, so that's going to be an issue. So for area of a semicircle, it's going to be 1/2 pi times the radius squared, right? That's our area of a semicircle. Half of pi r squared. Now, I still put an S right here. I don't have an R, but we'll get to an R. So you're going to have a little bit of an extra step right here. So if I'm looking at that S, I can do it just like we did our other problems. Right? So that vertical piece right there, I'm looking at the top minus the bottom. And so my top equation is my upside down parabola. That top equation is 2 minus x squared. And then I will be subtracting the function that I hit on the bottom here, which is just x squared. The problem will be easier to deal with if you simplify that a little bit. So it will be 2 minus x squared minus x squared. That's like 1x squared and 1x squared here. So I could write that as 2 minus 2x squared. Everybody okay here for my S? But semicircles, whenever you see that you have cross sections are semicircular discs, you got to be very careful because the equation of a semicircle doesn't use an S, right? It doesn't use that length across the circle. The equation of a semicircle uses a radius, and so the radius of that semicircle would only be from the middle of that line up to the top, or from the or to the bottom. It doesn't matter which side. That is your radius. How does your radius relate to your S? Okay, S is twice your radius. So if I want to write myself an equation for the radius, I just need half of S, right? Because it's radius only goes halfway across there. So I'd have 2 minus 2x squared divided by 2. Sometimes that will simplify, sometimes it will not. In this case, it simplifies really nicely to 1 minus x squared. So that's a step it's really easy to forget, like to forget to cut that s in half to make it a radius. And now it can go back into our area formula. So what we'll end up with for our area formula will be 1/2 pi times 1 minus x squared squared here. Stop for a second. See what questions you guys have. Good. All right, so we want to integrate this to get volume. So we will integrate 1/2 pi. It is going to be best here to go ahead and expand that out. So we're going to do 1 minus x squared times 1 minus x squared. I would suggest doing the square, double square. So it's going to be 1 minus 2x squared plus x to the 4th. What should our limits on our integral be? Okay, we are looking on the x-axis, so the furthest corner of that base is right here at -1, and the other furthest corner, furthest to the right, is over here at +1. So we want to integrate from -1 to 1. Not 0 to 2. 0 to 2 would be if we were doing this in terms of y. Okay. Now, in order to integrate this, I would take this 1/2 pi and put it on the outside because it's just a coefficient. So instead of distributing it and then having something more complicated to integrate with, I would just leave it on the outside because you can do that in this case. So you will have, is it all right with you guys if I write that as pi over 2? Right there, 1/2 times pi would be pi over 2. And then I'm going to integrate 1, which will just be x. Right here I'm going to get x to the 3rd minus 2 over 3. Right there, and then I'll get 1/5 x to the 5th. And this is from -1 to 1. So, this is probably the only one I'm going to do all the way out completely by hand. You're going to plug in 1, you're going to plug in -1. So the pi over 2 is just way out front here. And I'll have 1 minus 2/3 times 1 cubed plus 1/5 times 1 to the 5th minus -1 minus 2/3 times -1 cubed plus 1/5 times -1 to the 5th. So this is going to be 1 minus 2/3 plus 1/5. And this will give me -1. When I raise -1 to the 3rd, I still get -1. So that'll become plus 2/3. And same thing is going to happen right here with that -1 to the 5th. It's still going to be -1, so I'll get minus 1/5. But if I distribute that negative to everything, it's just going to change the signs back. So that'll be negative, that'll be positive. So I could go ahead and combine those together. So 1 and 1 will give me 2. -2/3 and -2/3 is going to be -4/3. 1/5 and 1/5 is going to be 2/5. At this point, we probably just want to get common denominators. We'll have 30 over 15 minus 20 over 15 plus 6 over 15. And that is going to give me pi over 2 times 16 over 15. The 2 and the 16 can reduce, and I should get 8 pi over 15. I definitely don't think they would go any more overboard with that and making you actually solve that down by hand. A lot of these problems are either just a setup or they're calculator active, so you can use the calculator to integrate with it. And that's probably the only one I'll have you guys do all the way by hand. Questions? Okay, let's look at another one. Okay, we are specifying the volume of a solid whose base is the region bounded by the lines 1 minus x over 2 and negative 1 plus x over 2 and x equals 0. The cross sections perpendicular to the x-axis are, I'm going to change this right here because I have not seen an equilateral triangle problem in a long time, and I don't think they're going to ask us that. So I'm going to change it here. So instead of saying equilateral triangles, let's say they are right. Actually, I think we need to use the word isosceles, right? Isosceles, right triangles. Hello? Yeah. You're up. It'll be the last of that worksheet you guys had last night, so you've already got what you need for that. Now I'm recording too. Alright, so isosceles right triangles with one leg in the base of the figure. Which is a good thing because that's going to be a lot easier than the equilateral there. So, let's think about these graphs right here. They gave these functions to you in a way that makes them look a lot more complicated than they really are. Because if I've got f of x equals 1 minus x over 2, what is another way I could write that? Particularly the x over 2 part. 1/2 x. So really it's 1 minus 1/2 x, which I could think of as negative 1/2 x plus 1. This is just a line, right? It's got a slope of negative 1/2 and a y-intercept at 1. Same thing for g of x. I've got negative 1 plus x over 2. So that's like negative 1 plus 1/2 x, which could be written as 1/2 x minus 1. So both of those are just lines. So if I graph those, x equals 0, what is that? Y-axis, right? So I really only need like the right side of the coordinate plane right here. And I don't need much room here because if I do my f of x is 1 minus x over 2, then I've got a y-intercept at 1 and a slope of negative 1 over 2. That would make this line right here. That's my f of x. And then my g of x has a y-intercept at negative 1 and a slope of positive 1 over 2. And that would be this line right here. That's my g of x. And then the x equals 0 is the y-axis. So the region that I'm using for my base right here is this triangle. So, how do I find, let's think about the cross section that they've given us. First of all, are we going to be in terms of x or in terms of y? If we are perpendicular to the x-axis. This is in terms of x. So if it says perpendicular, it is, so this is a dx problem. Which means that we want to think about like a vertical slice here. And what we're doing here is a little bit different than the squares. If I call that S, like I've been calling it, all right, just for some consistency here, then we've got a isosceles right triangle with one leg in the base of the figure. So this would be one leg of our isosceles right triangle. The other would have to be like sticking straight up. Right here, it's isosceles, so it would have the same length, and then we'd have that there, and that's like 3D sticking up off of that base. So if I want to find the area of that figure, what would I do for the area of that triangle? What? 1/2 S squared, because it would be 1/2 base times height, and your base is S and your height is S, so 1/2 S squared. And for a isosceles right triangle with one leg in the base, that's the formula you're going to use every time. So our S, we need to figure out what that is. It is going to be the top function, which is our f of x, which is 1 minus x over 2. Minus our bottom function, so that line S right there ends at the red graph, which is your g of x, which is negative 1 plus x over 2. It will be better for you to simplify that before you try to integrate, although I am going to let us use a calculator at the very end of this so that it doesn't take so long, so we could, I guess, do it the long way. So if we distribute that negative, we'll have 1 minus x over 2 plus 1 minus x over 2. And it is probably more helpful to think of that as 1 minus 1/2 x plus 1 minus 1/2 x. So if I put that all together, 1 plus 1 is 2. And I'll have a negative 1/2 x and another negative 1/2 x, and that will just give me a negative 1x. All right there. All right, now this needs to get plugged in for our s. So we're going to take this, we're going to plug it in for our s. Our area formula is going to be 1/2 2 minus x squared. And it's not that you couldn't do this with, you could definitely do this without a calculator. It wouldn't be any worse than like some of the first ones we did, but it gets tedious and I think not our best use of time. So I'm going to let us use a calculator for this. You're going to take 1/2 2 minus x squared dx. What do our limits on our interval need to be? What? Not negative 1, 1. That's from the y-axis. And this is a dx problem, so we need to be looking at the x-axis 0 to 2. So 0 to 2. It's probably one of the biggest mistakes that students make is they get their limits wrong because they look at the wrong axis for that. So we could do this by hand. It's not the world's worst. It's probably a little easier than the first one we did do by hand, but we don't want to spend all day doing this, so we are going to use the calculator to integrate. So we will have the integral from 0 to 2 of, this on the side here, of 1/2 2 minus x to the second dx, and I'm getting 1.3 repeating. Or you may see that written as 4/3. Okay. Questions? Web, it's going to be the rest of that worksheet, so you've already got what you need.
Whenever you I know you're putting like 2 dots and making a line to equal S, are we just randomly picking 2 dots or?
I'm just anywhere on that figure, because your cross section has to be perpendicular to the x-axis. It's got to be vertical. But I could pick any place in between here. I'm going to draw myself like a vertical line.
So if it says perpendicular to the Y,
we do a horizontal. Yes.
Parallel would be still.
Yeah, parallel to the Y is still
means
use x coordinates. So they usually use the phrase perpendicular. Occasionally they'll throw that parallel in there. So it's not necessarily at this point, but anywhere I choose here, the blue graph is still my top graph and my red graph is still the bottom graph. So you'll get the same thing no matter where you draw it in. Does that make sense?
It's top minus bottom.
Top minus bottom if it's in terms of x. Right minus left if it's in terms of y. All right. Let's skip number 3. Let's go to number 4. Because having the hypotenuse in the x-axis makes it a lot more difficult. And again, I haven't seen a lot of those problems in a while. Although I might should check your homework, but I don't think. Make sure that's not the case. Oh, I do have an equilateral triangle in your homework. I may just change that one. I think I'm going to change one of those in your homework for that. The base for a solid is bounded by y equals x to the third, y equals 0, x equals 1. The solid is formed with semicircular cross sections perpendicular to the y-axis. We're supposed to find the volume of the solid. Since this says perpendicular to the y-axis, is this a dx problem or a dy problem? Dy, because we're perpendicular to the y-axis this time. So it's still probably best to get a graph for this. Sometimes I like sketch what I've got. A cubic looks like this. Y equals 0 is the x-axis. X equals 1 would be over here. So it's really first quadrant. That's what I need over here. And for a cubic, all you really need to graph for this cubic right here is 0 cubed is 0, 1 cubed is 1. It's going to look like this. We would have y equals 0. That's the horizontal line at 0. That's the x-axis right here. And then x equals 1 is the vertical line right here. Now, because this is going to be a y-axis problem, dy problem, I can't have y equals x to the third, right? Because I need everything to be in terms of y. So I need to take y equals x to the third. I need to take the cube root of both sides so that I get x equals the cube root of y. So rather than calling this y equals x to the third, I'm going to call it x equals the cube root of y. Sometimes they go ahead and give you the equations already solved for x, and it makes it easier, but they did not on this one. And we will be looking at this little area right here for our base. My red line's kind of off right there. In this case, we are taking a horizontal slice right here, which, because we have done it over and over again, I'm going to call S. So, we need to think semicircular cross sections. Area for a semicircle is 1/2 pi r squared. It's important to remember that is r, not a s. So we can't just plug an s in, we got to adjust a little bit. But we're going to find our s first. In this case, because our s is horizontal, we are doing furthest to the right minus furthest to the left. So our right end point of that little line is on my green graph. What's my equation for that? X equals 1, so I'm just going to get 1 for that. And then my right end point is over here on the blue graph. And I'm going to use the cube root of y, not x to the third, because everything needs to be in terms of y. So I have cube root of y. Can't really simplify that. On all the other problems, I just go to plug in this in. But does my formula right here use a s? It does not. It only uses a radius. And the radius, because what we're going to be doing here is we're going to be making like little semicircles right here. That radius is only half of my s. So I need to first say that the radius would be 1 minus the cube root of y over 2. And then I can plug that in up here. So my area formula is going to be 1/2 pi times 1 minus the cube root of y over 2 squared. And again, it's not impossible to do this by hand, but I think it's going to take a lot longer than the value of doing it by hand here. So I'm going to let you guys use the calculator for this. So I would integrate 1/2 pi 1 minus cube root of y over 2 squared with respect to y. What should I use for my limits? 0 to 1. This is kind of a forgiving problem because, Joshua, where did those limits come from? Yeah, they could have came from either axis. We are looking at the y-axis, but they are the same on either axis. On the 0 up here to 1 is what we're supposed to be looking at. You could have looked at it wrong and still got the right limits because on the x-axis it's also 0 to 1, but it's not really what we're looking at. So we are just going to type this one into Desmos here. So integral from 0 to 1 of 1/2 pi of 1 minus the cube root of y over 2 squared think that is raising it to the second power because I typed it in. It looks like it's just multiplying by 2. But I'm going shift. Pretty sure that's raising it to the second power. Feels too small, but I guess this is a tiny little area here. Because even your base would be like less than 1, right? And then, yeah, I think this is okay. So we're getting 0.039. Questions? Alright, so we got a little bit of time to work on this. Number 4 I really could have given you last night. I wasn't paying attention whenever I told you which ones to do. I thought I remembered it correctly. So number 4 is not a triangle or semicircle. 5 is just a regular problem that I want you to do. 6, I'm going to change the problem. It means your answer choice. Oh, I forgot to show you this. I'll show you that in a second. 6 is I want to change the problem. It means your answer choices are not going to be right, so just work it out and get the answer for that. So where it says equilateral, on number 6, where it says equilateral triangles, I want you to change that to isosceles. Right triangles with one leg in the base. Everything else about it can stay the same, but make those isosceles right triangles with one leg in the base on number 6. Your answer choices won't be right, or probably won't be right anymore. And then 7 has a quarter circle, which is different, but I want to leave that and see if you guys can figure it out. Okay, taking those same principles that we've been using. It'll be different, but try that one. So, we'll just spend the rest of the class working on this. If you got questions, I'll be around. And if you are desperate for test corrections, yes, you can do that.